Okay, so our final speaker this session is Humphrey Burchell from the University of Kent, talking about how to make programs slow down reliable. Take it away, Humphrey.
Thank you. Yes, and also I mentioned I did this work with Stefan as well. So why would you actually want to make a program run slower? Well, there are actually a variety of use cases. Profiler accuracy. When you actually want to evaluate the accuracy of a profiler, you might want to use such processes as causality analysis or profiler divining, which is an approach that we've proposed in a UPSLA paper, which I recommend you come to my talk on Saturday, and I'll explain more about how that actually works. Exposing race conditions, it's terribly useful if you can make certain sections of a program run slower than normal, and this can help actually expose situations where a race condition could occur. Implementations such as chess or waffle actually use some form of deliberate slowdown to actually create race conditions or see them. And finally, virtual speedup. This is a proposed technique implemented as COS. What they do is deliberately make sections of the program run slower, and then this actually lets them see optimization opportunities from the sped up code, which is just the code that isn't slowed down. And they would definitely are after a reliable and accurate slowdown. So the goal of the paper and this talk is actually we're going to evaluate x86 instructions and see how good they are for being used as actual deliberate slowdown. The requirements we have for each instruction is how accurate are they. If we want to make the program or a basic block run 100% slower, can they actually get to that level of slowness, and how reliable are they of being that slow? Side effect free. You don't want to add instructions and then you've changed the performance behavior of the program. You don't want it to now run differently. Particularly for stuff like COS or profilers, if you're trying to check how reliable the slowdown is, you don't want one method to now be the entire execution when it's slowed down, but not when there is no slowdown. And distributed slowdown. You don't want to achieve slowdown by actually just making one single block consume the entire slowdown execution. You actually want to try and distribute it and make all areas of the program run slow, but at the same level. We're going to achieve slowdown at the basic block level. Basic blocks are just general ways to organize machine code. They have one entry point and one exit, so there will only be one jump. Why it's useful to use these for slowdown is once you've actually added slowdown into a block, if that block is executed, the slowdown is guaranteed to be executed. So it's a good area to target slowdown. We're also working very, very late into the compiler, almost the last optimization phase. So we're working nearly on the final emitted machine code, which means we're avoiding interfering with compiler decisions such as inlining or dead code elimination. So inserting shouldn't have an effect on decisions and therefore change the program behavior. To actually determine how much slowdown to add, we're using hardware counter feedback. We used vTune, and we added slowdown into a block and looked at a vTune report and see how much increased amount of time did we add to that block, and then we just iteratively added slowdown until we could get as close as possible to a target slowdown. Our setup, we're working with Java and the Graal compiler specifically. We're making use of compilation replay, which is where you do an execution and it logs how it did what compiler decisions it made. You can then refeed those decisions, and then the compiler will try its best to try and repeat a similar execution. This should hopefully remove a lot of noise and non-determinism we would see in our results. And we're using the RWFastJet benchmark suite. Specifically, we're actually only using one deterministic benchmark. We're using the Towers of Hanoi benchmark. We only did one benchmark because the setup time and that iterative approach of adding slowdown is extremely time-consuming, so we thought only one was appropriate. The actual proposed x86 instructions we looked at were NOP. NOP has 0 side effects, and it's pretty much purpose-built for such things as delaying or padding. MOV MOV is probably one of the most used instructions in x86. It's very fast, it's very highly optimized, and if you use it in the sequence of moving from one register to the same register, so for example a MOV racks, you don't actually change the value inside the racks register, but the CPU has to waste some time actually dealing with that. Push and pop, after the sequence, nothing has actually changed, so this is a more heavier slowdown sequence that you could use, and we want to see that maybe a large amount of slowdown can get you to that target quicker. SFence, it's a single instruction, serializes delay, but it shouldn't actually have any effect after it's actually executed. Long push and pop, this is just a longer sequence version of a push and pop, but we actually make use of vector instructions. So this is actually to see if we kind of load some of that time to the vector unit, maybe that gives us a different level of granularity of slowdown. And pause. Specific to x86, it is a purpose-built delay. It's used to hint the CPU of spin waits, busy loops, and we thought it would be an appropriate instruction to test for this use case. The research questions we had in the paper was how close does each candidate get to the target speed? So we set a target speed of 100%. Could we get the program to run 100% slower? What distribution among the basic blocks? So to actually achieve that slowdown, we make each individual basic block of the program run 100% slowdown, so therefore the program should run at 100% slowdown. And we wanted to see, is that slowdown actually achieved among all blocks, or has just some blocks got very slow and that's just achieved it? Do they maintain the original performance behavior? This is to test whether or not the slowdown has side effects. What we did was we pointed a profiler at the program with no slowdown and then with slowdown, and we wanted to see, has the profile changed in any degree? And finally, an extra question we tested in the paper, but we won't in this talk, is what effect does the placement of have within the blocks? If you have a basic block and you have many slowdown instructions inserted, should you place all of them at the beginning of the block, at the end of the block, or should you try and mix them in the block? They're all guaranteed to be executed, but what effect does it actually have if you distribute them amongst the block or at the start or the end? So, how much slowdown did we actually add? So for the Towers of Hanoi benchmark, there are 53 basic blocks that actually consume some amount of execution time. We set a target speed of 100%, and we required that each basic block had at least a minimum of one slowdown. NOP and MOV clearly have far more amount of slowdown. This sort of starts to hint to the degree of granularity we actually had with slowdown with the NOP and MOV. It required far more to get to that target speed, but they have a finer granularity. SFence and pause, you can see it's nearly about one slowdown per basic block. So one was already enough to get to the slowdown or exceed that target speed. But actually, what was the program overhead? So for 100%, we saw that NOP and MOV get pretty close to that target overhead of 100%, 109, 106%. Push and pops around 202, and SFence and long push fence around 400. This sort of suggests that they actually, using those types of instructions, have a minimum amount of overhead that they're adding. Adding just one to a basic block already makes the block slower. So if you actually wanted to achieve a target slowdown of 100% or less, then these instructions are probably not suitable. Pause, very much far off. 11,000% overhead was added to the program by just adding one pause to each basic block. It's clearly not very suitable for any use case that we would for these benchmarks. What was the distribution? So we're plotting here the difference in overhead from the target overhead at 100%. So we're hoping to see that the majority of the runtime is somewhere around 0, which is 0 difference from 100%. NOP and MOV have definitely a shape that we're looking for. Most of the runtime is distributed around 0, and they've got quite a symmetrical shape, which shows that we had a few blocks that were slightly underslowed, but we also then had some blocks that were slightly overslowed, so it started to balance out. Push and pop, you can start to see that it's getting that there's many blocks, and therefore the runtime is starting to get overslowed, and that's shifting to the right. More clearly with SFence, that it's just lots of the blocks are getting overslowed, and pause pause caused so much slowdown that it's just over the bracket and over 500% difference. Do they maintain the original program behavior? So we pointed a sampling-based profiler, async specifically, at the program before slowdown and after slowdown, and we looked at the percentage of runtime each method had. So even though the program is running 100% slower, you would still expect each method to be the same percentage of runtime. So therefore, the methods we would expect to be on the x equals y line. North and mov, the percentage of runtime has stayed very similar with the program being slowed down, so you've got some confidence that there's very little side effects there. Push and pop, you can start to see that there's definitely change in the program behavior, similar with S-fence, and long push and pop has definitely completely changed. Interestingly, pause has not changed to such a degree, even though it had such a massive overhead. One likely explanation for that is because those pause operations are so heavy in terms of cycle cost, you've now just biased it to activation count of the blocks, and that has just led to a profile that is slightly similar to what it's before. But there's still definitely a difference and a change in the program behavior, so it's not very suitable for it anyway. And a use case. We actually have used this to implement profiler accuracy evaluation. For our paper that we're giving to Uppsala and my talk on Saturday, please come, we've made vector.hasSum actually run slower. We've added 5 seconds of additional runtime onto vector.hasSum, and then we're testing with 4 profilers, have they actually detected this change? Async, and the red dotted line is what we predict the change to be. Async and JFR, Java Flight Recorder, have actually detected this change in runtime, but JProfile has not detected any change in vector.hasSum, even though it's running 5 seconds slower. And YourKit has not also detected a change in that, and maybe actually is slightly decreased the amount of runtime. So this has actually allowed us to evaluate these profiles and their level of accuracy, with async and JFR for this one experiment having good accuracy, but JProfile and YourKit not so. To conclude, we found that NOP and MOV were the best instructions in terms of accuracy and side effect free and maintaining the original program behavior. Not shown here, but in the paper, we actually found that mixing the slowdown amongst the basic blocks was the best approach compared to putting them all at the start and all at the end. And this actual approach has enabled us to implement a viable approach to evaluating profile accuracy. Thank you. That is the end.
Thank you, Humphrey. Okay, questions, please head to the mic.
Hi, thanks for the talk, a very interesting premise. This is Manas Thakur from IIT Bombay. The question I have is, have you implemented it, you implemented it in Graal, but is there a way the programmer or the developer could specify an interface through which they can, where do they want a slowdown in the program, for example? Or do you plan to work on it, if not?
If I understand your question right, if you're asking about generalization, it's not specific to Graal, but we did it in Graal.
Yeah, but let us say as a programmer, I now want to specify what parts of my program do I want to be slowed down using the NOP or move instructions.
Yeah. Could you actually build an interface to actually allow you to do that?
That's the question.
Yeah. Yes. It's going to be very difficult. So we did it at a basic block level, which meant we didn't actually have to care how this actually returns to source. And it's very difficult to then map that back. So yes, you could do it. You're going to have to solve the problem of knowing which bits of the original source code then actually turn into basic blocks. And basic blocks may contain multiple methods due to inlining. So you have to decide at what point. So yes, it is possible. That is the difficulty, and that's why we chose to do it right at the end when it's just basic blocks.
Okay, thanks.
Hi, thanks for the great presentation. I'm curious how sensitive this is to variation within x86. So I imagine you were testing it on a specific CPU, but obviously there's oftentimes quite drastic architectural changes between CPU generations, or even, I guess, between manufacturers. How sensitive is your testing to such variation?
So we did test this only on one x86 CPU. I would imagine if you move to a different architecture or different CPU alone, you would have to redo that calibration again. It does just use hardware counters, so it should be transferable. But yeah, I would expect it won't. You can't just transfer that out of the box to a different CPU. You'd have to do it all again. You have to retune, redefine.
I see. Thank you.
Thanks for the talk. So a single basic block doesn't necessarily take a consistent amount of time to run because of things like cache misses and things like that. Did you consider how you would deal with that at all?
So that's why we used the hardware counter feedback. So we originally did build some system where we had a static guess. We knew the cycles and we had a guess at how much to add, but that just doesn't work at all. Yeah. So we had to use the hardware counters to actually incorporate that pipelining and out of order execution, so the value adjusts.
Did you consider how you might deal with something where, like, a specific basic block takes a different amount of time depending on, like, whether how it?
Yeah. We didn't really encounter too many of those. In the other work, there are cases where you get a basic block which is just a test and a jump, and they do just completely change from costing a few seconds, a few milliseconds to a few seconds. Those ones you have to bite the bullet. You have to just accept that it's not going to work. And then that's where you get the variancy. It's if there was a case where that was a majority of the runtime, I think there would be a problem. But we didn't encounter that. It was only a tiny amount of the runtime accounted for those really wobbly basic blocks.
Okay, thanks.
Hey, thank you for the great talk. I mean, if you read the Intel if you read the Intel manuals, I guess they have some explanation on the number of cycles and about the performance of each instruction. So, how much were you surprised by the results if you read the Intel manuals compared to what you got?
I was surprised how stable the blocks are. Very related to the previous question, there is majority of the time the blocks do stay actually a very similar execution amount of time. Interestingly enough, single byte NOPs got completely eliminated immediately, whereas 2-byte ones got saved. But I think that was very specific to our version of it.
And for instance, for the pause instruction, did you expect it to be like that?
For the what instruction, sorry?
For the pause instruction.
For the pause
After
instruction.
Reading the manuals, did you expect it to be like that?
No. There's nothing in the manual that hints to that should happen. I remember the Anger Fog data says that it doesn't take. It's like 20 cycles or something. It's nothing huge, but clearly it's just not usable at all. Okay. So yeah, that one definitely surprised me a lot.
Okay, thanks.
Thanks for the talk. I'm wondering if you've generalized this to programs that will run on multiple cores, and whether that would change the instructions you use for slowdown, because SFence obviously would change the ordering sort of thing. But have you generalized this to other sorts of programs?
So no, we haven't done that yet. I would be really interested to see what effect that actually would have specifically with SFence, but luckily, well, we found NOP and MOV were really the only viable implementations, and for the other work we actually used the MOV with a similar register.
Yeah, I wonder if there's a specific angle for this where you would like to sort of focus on the synchronization instructions and make those specifically slower when doing sort of multi-core sort of programming.
Yeah. Obviously we haven't done it, but I would be really interested to see if that is a viable thing to do.
Thank you.
Okay, I think that's the end of the session. So let's